Okay, thank you, Will, and thanks for the invitation to speak today. This is my second Zoom talk now, so I'm getting the hang of it a bit, but it's still a little strange not being able to see everybody in the audience when I'm talking to you. Um, so today, this is a talk that'll be just like Jessica's talk yesterday and Ofer's talk. It's not exactly on Hamilton-Jacobi equations. But I'll be talking about discrete regularity for graph Laplacians with a mind towards applications in data science. But at the end, I promised to come around and I'd talk about some connections to homogenization, maybe percolation theory, which is more of future work. So let me just start talking about graph-based learning a tiny bit. So we start with a graph xw. So x are the vertices, w are non-negative edge weights. We take every pair of points to have an edge weight, where 0 edge weight would mean there's no edge between the 2 points. You can think of the vertices as lying in Rd, but it's not necessary for the first part of the talk. In a data science or machine learning problem, we often give data the structure of a graph. This is a good way to encode similarities between nearby neighboring points. In this case, the weight wxy is large if the two data points x and y are similar, where you have to provide the notion of similar. And it should be smaller, it should be 0 if they're not similar. Generally, you want a graph that's sparse, that has very few edge weights that are not 0. So common tasks you would apply graph-based learning to are clustering or semi-supervised learning. Clustering is a problem of grouping your data into clusters or groups that contain mutually similar data points. And semi-supervised learning can be thought of as sort of clustering where you have some additional label information that's given about the data. So for instance, as a concrete example, say I have a data set of a bunch of handwritten digits from 0 to 9. So one example is the standard MNIST data set that has 70,000 such images. Here's a grid of just 100 of these images. So each image is 28 by 28 pixels. So I can think of that as a vector in R 28 by 28. So that's R 784. So it's a vector in a fairly high dimensional space. And so on this data set of 70,000 images, so 70,000 vectors in R784, I can build a graph. And so one way to do it is to construct geometric weights. So between two images x and y, the weight in the graph is some kernel function I choose eta, which is often Gaussian, applied to the distance between x and y, which can just be Euclidean distance, divided by some bandwidth parameter epsilon. In practice, you might also tune epsilon locally in the graph. So you could choose epsilon to be something like the distance to the kth nearest neighbor of x, and you get a k nearest neighbor graph. Okay. So once you build a graph, you can address a problem like clustering, for instance. So here's a picture of what clustering would look like for MNIST. You would try to group the digits into clusters that have similar features. And so the hope is that these would be, you would get all the ones together, all the zeros together, so on. And so you can see here, this is an actual clustering that's obtained by some algorithm. I'm not sure which one it is at this point, but you can see the ones are pretty well clustered together over here. So the zeros are pretty well clustered, but some of them that look similar, like 9s and 4s, are mixed up a bit together over here, and so on, 8s and 3s. So one can ask, how do you do clustering with graph data? Okay, how does one do this? So one of the sort of most appealing, I guess, or simplest to write down formulations is like a graph cut energy. So you can say, I want to look among all partitions of my graph, and let's just look at binary clustering. So we just want to partition the graph into two classes. And so among all partitions, so among all subsets A of the graph, I want to look for the one that minimizes the graph cut energy. So I'll call it cut of A is the sum of all the edge weights you'd have to cut if you were to partition A and A complement. Okay, this is actually very easy to solve, this min-cut problem, but it tends to produce unbalanced classes. So there's no incentive for it not to just pick the set A to be one outlier that has very few edges connected to it, and take A complement to be everything else. And this is not the kind of clustering that you're looking for. So normally one looks at a balanced cut where you minimize the ratio of the cut energy to something that prevents A or A complement from being too small. And so you can take the product of volume of A and volume of A complement, say. But there are several other ways you can balance the cut energy. This is great and actually produces really good clusterings, but now it's an NP hard problem. So when you're faced with hard computational problems, what you do is look for ways to relax the problem. And this will lead to spectral relaxations. This is the direction that we're heading. So to see how this works, let's rewrite the graph cut problem, where I write it in terms of the characteristic function for the set A. So I take a set A, it has a corresponding characteristic function u of x, which is 1 inside A and 0 outside. And the cut energy in terms of this characteristic function looks like a Dirichlet energy on the graph. It's like 1/2 sum of the squared differences ux minus uy squared times edge weights. And you can write volume of A in terms of the characteristic function too. So you get a problem that looks, kind of like a Rayleigh quotient or something, right? So you're minimizing a Dirichlet energy divided by some kind of norm of u. The reason why it's hard is that you have this binary constraint that the values of u have to take on zeros or ones. And so this is a non-convex combinatorial constraint that is very hard to satisfy. So the relaxation is to say that the function u can take real values. Okay? And then you write down almost the same thing, but you actually turn it into a Rayleigh quotient. So you divide by the L2 norm of u. And of course, to make the solution non-trivial, we should say it's orthogonal to constant functions. And so this is exactly this solution to this relaxed problem is exactly just the first non-trivial eigenfunction for the graph Laplacian. This is called the Fiedler vector. And so this is a widely used algorithm for clustering. So this would be called binary spectral clustering. So you compute the Fiedler vector, and you take the sign of the Fiedler vector for the set A and for A complement. You can extend this to clustering into more than two groups. And the way this generally works is that you compute the first k eigenvectors for the graph Laplacian, and you normalize them, and you call them u1 through uk. And then you do a spectral embedding of the graph into RK. And the spectral embedding psi works by associating each vertex of the graph with the vector in RK whose values in the coordinates are the values of the eigenfunctions applied to that vertex. And so the spectral embedding takes your graph, which might originally be in a very high dimensional space, or maybe it's not even embedded in RD. It takes the graph and it embeds it into a low dimensional space RK, maybe K is 5 or 10 or something very small. And then this gives you a point cloud in RK, which you cluster however you like. And so often people will use a k-means algorithm to cluster at this point. So these kinds of spectral methods are very, very widely used in machine learning, not just for clustering, but also for dimension reduction. So just working with the spectral embedding itself can be used in semi-supervised learning and lots of other problems. The main references for spectral clustering are this paper by Shi and Malik and by Ning, Jordan, and Weiss. And the dimension reduction versions are sort of the Laplacian eigenmaps and diffusion maps. This is by Belkin and Yogi and by Koifman and Lafon. So for example, if I take the MNIST data set, and here just to make things easier to visualize, we'll take a subset. We'll just take the digits 1 and 2. And so there's about 12,000 of those. Right? And so here you would expect to get a good binary clustering into the 1s and the 2s. And so what you're seeing here is the spectral embedding of the 1s and 2s from MNIST into R2. So it's a two-dimensional spectral embedding. And so the x coordinate along the x-axis is the Fiedler vector, and the y coordinate is the next eigenfunction. And you can see it nicely sort of clusters into two groups. It's not like a mixture of Gaussians. It's not very nice for k-means, for instance, but you have this one long cluster over here, and you have this one small cluster on the right. And you can ask, is this, if I were to separate this by a half space, let's say, and get two separate clusters, is this a good clustering for the data set? And it turns out it is. So if I color the points based on if it's a 1 or a 2. So the digits 1 correspond to the blue points and the 2s correspond to the red points. You get almost a perfect clustering into 1s and 2s if you were to try to separate this by a linear space, let's say. So these methods are very, very useful and very powerful in machine learning. Let me mention they've been used in other contexts too. So for instance, the spectral clustering was some variants were originally proposed for image processing to segment an image into sort of foreground, background. In a separate project, we have so this separate project is focused on analysis of broken bone fragments, which occur sort of in an archaeological context. And so this is a small broken bone fragment from an elk. And one problem you might want to address here is to segment the broken bone fragment into faces separated by break edges. And so we've applied spectral clustering to this kind of problem with pretty good success so far. So we build a graph over the bone fragment, which is a 2D triangulated mesh. We build a graph by connecting nearby points within some ball epsilon, but the weights are not geometric weights. The weights depend on the difference in the outward normal vectors to the surface at those 2 points. So the weights would be small across an edge, and they would be large within a face, let's say. And then we use the standard spectral clustering algorithm. So let me say, because of all this interest in spectral clustering, there's been a lot of work over the last decade or so on rigorous analysis of the spectrum of the graph Laplacian. And in order to do this, you have to make some assumption on the data. Generally, if you want to study graph Laplacians, you can't study just general graphs because this is too abstract and too large of a class. So there are various sort of models that people take for graphs. There are sort of random geometric graphs that we'll talk about in this talk, but there are also stochastic block models that are also popular. So so we will talk about the random geometric graph, which comes from the manifold assumption on your data. So even though data lives in a very high dimensional space, like in the MNIST example, data lived in 784 dimensional space, which is huge. We expect, or at least data scientists, machine learning people, expect that the data actually lives on some much lower dimensional smooth manifold embedded in that high dimensional space. For MNIST, for instance, it's estimated that the submanifold, if there is one, maybe it's a union of several or something, it's estimated to be about 10 to 12 and not 784. Okay, so we take M to be this compact, connected, orientable, smooth, M-dimensional manifold embedded in RD, and we think of our data as being drawn from this submanifold. And we have the usual notation. So there's a Riemannian structure induced by the ambient space RD, and we have a geodesic distance between points x and y, which is dm of xy, and there's the ball of radius r centered at x on the manifold, and we have the volume form and so on. Okay, so we have all the standard things on the manifold. So the assumption is that our data is an IID sample from some density function rho on this manifold. So rho should be sufficiently smooth. So for most of the talk, C2 is fine, but there's no problem assuming more regularity if we need this. Okay, so we have an IID sample from the manifold, and we're going to build a graph over this IID sample. And we'll choose a kernel to build the graph. So the kernel will be used to define the edge weights. This is just any non-increasing function that has compact support. So we'll say it's 0 outside of the interval 0 to 1. And we assume it's Lipschitz, and it integrates to 1 to make things work out nicely. And then given a bandwidth, the weights in the graph are just given by the kernel eta applied to the Euclidean distance between x and y divided by epsilon. And the key point to make here is that we're using the Euclidean distance in the definition of the weights, even though these points are sampled from the manifold. And the point is that in the data science applications, we don't know the underlying manifold, so we have to we can only use ingredients that we know to build the graph. And so this is Euclidean distance. Okay. So of course, locally, this is well approximated by geodesic distance, anyways. So the graph that we get in this way is called a random geometric graph, and there's been, this is a central object of study in many different fields. So it's known, it's been established for more than a decade, let's say, that the spectrum of the graph Laplacian on random geometric graphs, it converges in the large sample size limit, so that's n goes to infinity, and the bandwidth goes to 0. It converges to the spectrum of this weighted Laplace-Beltrami operator. So it's not the usual Laplacian, it's weighted by the density, rho squared. So you can think this is like you have faster diffusion in denser regions of the graph, or you can think if you expand the divergence, you get a drift term that looks like the drift in the direction of the gradient of this function rho. So here's a brief list of the spectral convergence results going back to the work by Belkin and Yogi in 2007. Some of the results have convergence rates. I've tried to illustrate this in the list, and you see various rates. They're all in terms of the number of points n. And so for all these rates, we take sort of the best choice for epsilon, the smallest possible, so that the rates hold with high probability, and this gives you the optimal n. So some of the maybe the most recent breakthrough was maybe this paper by Nicholas Trilos and Gerlach and Hein and Slepchev in 2018, where they introduced a new gamma convergence approach to prove convergence, or to prove spectral convergence, and they got at the time the sharpest rates for eigenvector convergence in L2 of this n to the -1/4m. In a follow-up paper that I wrote with Nicholas Trilos, we got a better convergence rate in L2 by combining the sort of variational gamma convergence framework with some more PDE tools, including pointwise consistency of graph Laplacians. And then in the meantime, we've been working on an L infinity rate, because so far this was not known. And I'll talk about that in the talk today. But then a very, very recent paper just in the last few months came out, well, I guess in the last few months of 2019, came out proving an L infinity rate, but much worse than the L2 rate. Okay, and I'll talk later in the talk. We can get the same rate for L infinity as we have in L2. And there are also some non-probabilistic results. So these are all random geometric graphs. There are some results where the graph Laplacian is studied, except the graphs are not random geometric graphs. They're instead sort of more from the numerical analysis point of view. You can construct a graph from a random point cloud, or from just an actual chosen point cloud that has nice properties. So you can ask that your point cloud is like an epsilon net or something. So the points are more uniformly spread than they would be for IID random variables. And there are some papers along these lines too. Okay, so one of the reasons why these results are still not sharp, let's say. So even though we have these sharper rates in our recent work, these we still don't expect that they're quite sharp. We should be able to knock off the 4, let's say. But one of the reasons why we see these worse rates, or we see no rates, we see some reasonable rates, we get better rates, and so on. This is only very, very recent work. One of the reasons is that it's kind of challenging to analyze these spectral problems on random geometric graphs, because we don't have a lot of the useful PDE tools that you would have in the continuum setting. So this is basic things like elliptic regularity and stuff. You don't have these for graph Laplacians, and so you're kind of handcuffed with what you can do. The second thing is that even when you apply these tools in the right way to control the average, control the randomness in the graph, there are some more complicated ways in which the graph randomness is averaging out. And so this is, I'll connect to this at the end of the talk, but there's some kind of homogenization going on at small length scales in the graph that produces much sharper convergence rates numerically than we can prove theoretically. And trying to understand this disconnection is an important problem, I think, in this area. So the question sort of for today is or that I'd like to pose in general is what kind of PDE tools can we push to the random geometric graph setting? And so I'm thinking about things like elliptic regularity. So the talk today will be about Lipschitz regularity. So I'll basically be looking at graph Poisson equations. Laplace u is equal to f, and this will include eigenvector problems, because I can take f to be lambda u, say. And we want to be able to estimate the Lipschitz norm of u in terms of quantities that involve f and u, let's say. And so this is, and after we do this, we're going to then show that we'll immediately get improved spectral convergence rates from these estimates. So this is a joint work with Nicholas Trilos and Marta Lewiska, and our paper is in preparation here, Lipschitz regularity for graph Laplacians. So let me just jump to the main results. So we have the manifold assumption, like I said before. So the points are sampled from an underlying smooth manifold. And we have the graph Laplacian constructed with the random geometric weights. And I take the normalized graph Laplacian. Okay, so the normalization, what you can think is that The n epsilon to the m is just making this into an average. So the number of neighbors, so you're just summing over neighbors in an epsilon ball. The number of neighbors is on average n epsilon to the m. So that's going to average this, or turn this into a real average. The 2 is this extra 1 over epsilon squared is because this is a second order scheme. And so really you should be dividing by length scale squared as well. So if you normalize this correctly, now what you can say, our first theorem is that with high probability, that you can estimate for any function on the graph, you can estimate its Lipschitz constant, right, by the infinity norms of u and the graph Laplacian of u. And it's not exactly the Lipschitz constant, so I put in red here this epsilon. All of the results that I'll write down have an extra error term, order epsilon. So basically, you can't resolve the regularity of the function on the epsilon length scale. You have to look on larger length scales. Everything holds with the high probability, but the probability is only sort of for selecting the graph, and it's independent of the function u that I'm writing down in this estimate. So this is a global result, by the way. So this is on the whole graph. If I have control over u and the Laplacian of u, I have a control on this approximate Lipschitz constant. And by the way, all of the results I'm talking about here, they're not new results in PDE theory. So these are all things that if I was looking at a continuum PDE on the manifold, these would all follow from standard PDE results. But these are results that in the graph setting are not known, at least to our knowledge. So you can also prove interior versions of these results. So sometimes you may have boundary conditions in the graph. You might not be able to control the Laplacian everywhere. So we can prove that if you want to estimate the Lipschitz constant of u in a ball of radius r, you can do this in terms of the quantities u and Laplacian u on the ball of radius 7r, let's say. Maybe the 7 is not optimal. Maybe you could do better than this. So you can immediately, I mean, if you go back to the first result, you can just take an eigenfunction of the graph Laplacian, and this Laplacian u becomes lambda u, and so you have a result for graph Laplacians, or for eigenfunctions of graph Laplacians. But it'll be in terms of the L infinity norm, which then you have to bound, because for the eigenfunction, you only know that it's normalized in L2, so it has L2 norm of 1, but you have to get the infinity norm bound as well. So we can essentially do that, and we can improve the dependence on u to the L1 norm in this estimate. So if I have an eigenfunction for the graph Laplacian, then its Lipschitz constant depends essentially only on the eigenvalue, okay, like it would in the continuum. So you know, I would have L1 norm is less than 1, let's say, if I had an actual eigenfunction. This theorem applies to general functions that are sort of approximate eigenfunctions in the sense that I can control the ratio of their graph Laplacian to the function u. And so a corollary of this is that for eigenfunctions, you can control essentially their L infinity norms by their L1 norms with a constant that depends only on the eigenvalue itself. Okay, so these are estimates that are, you know, that are very, very useful, or we've found them very useful for analysis of graph Laplacian learning algorithms. But these estimates did not exist in the graph setting prior to our work. So as a brief example, and we have in mind lots of other applications, but as a brief example of the applications of this, we can immediately improve the spectral convergence results. So we have this weighted Laplace-Beltrami operator, and the kinds of results you see, okay, so you might have multiplicity of eigenvalues and so on, so you have to be careful how you state these theorems, but the general framework is that I take some eigenvector of the graph Laplacian, un epsilon, and then with high probability, there's a corresponding normalized eigenfunction for the continuum operator, which is close within order epsilon. And the rate that we prove is essentially an order epsilon rate for like the C01 norm. So it's a C01 convergence rate, except it's approximate C01 because the Lipschitz semi-norm of u has this plus epsilon down here. Okay, so it's like an approximate C01 convergence rate. If you take, so this is for any choice of epsilon, right? So n is fixed. You can choose anything for epsilon, but you need this to be a probability that's close to 1 for this to be useful, right? So in this exponential here, the n epsilon to the m plus 4, it has to be large, let's say, to make this probability close to 1. And it has to be larger than a constant times log n to absorb these terms over here. So the smallest you can choose for epsilon is something that satisfies n epsilon to the m plus 4 is c log n. And this gives you a convergence rate up to log factors of n to the minus 1 over m plus 4. That's where these kinds of rates come from. Okay, so we get this for this was the L2 rate I mentioned before from our previous paper. We get this for L infinity and for the approximate C01 rate. Let's see. So what I'd like to do in the talk is to briefly outline sort of the proof of these results, and then talk about some future work at the end. So the main outline of the proof is that there are two parts. The first part is that we have a new method to lift this problem sort of from the graph to the manifold. Okay, so it's much easier to work with like non-local operators on the manifold in place of operators on random graphs. And so we have, which I'll like say in the next couple of slides, we have a new technique to extend the function from the graph to the manifold in such a way that you can control this non-local Laplacian by the graph Laplacian. And so it turns out this is sort of the correct non-local Laplacian to work with. It's essentially the graph Laplacian, but I've replaced the sum by the integral, and I integrate against the density rho. Right? And you see the geodesic distance here in place of the Euclidean distance. Once we lift it to the non-local operator on the manifold, now we can work with proving a Lipschitz estimate for this non-local operator. And there's lots of literature on regularity for non-local equations. So for this equation, we didn't find anything exactly useful in the literature, but so what we did was we used this method of coupled random walks, and so it's essentially this reflection coupling of Linville and Rogers, which with some additional ingredients to handle the drift term. So the random walk corresponding to this, so the random walk which has this as the generator, it has a drift that is influenced by this data density rho. So it has a drift in the direction of higher density, let's say. And so this requires some extra ingredients over the original reflection coupling methods. So I'd like to talk about these, but I'll talk about the interpolation stuff first. Right? So let's talk about lifting to the manifold. So let's go over some very basic stuff first. I have this graph Laplacian, which, even though it looks kind of complicated, it's just a sum of IID random variables. So I'm going to say that I have a smooth function u in the continuum that I restrict to the graph. And so this is just a sum of IID random variables. And so I can take its expectation, and I get immediately this kind of non-local operator. Okay, so this is how you can see where this non-local operator comes from. Of course, you want to control the fluctuations between the graph Laplacian and its expectation. And so here you can apply standard concentration of measure results. The correct thing to use here is Bernstein, because the variance, these random variables are very sort of locally concentrated around the point x in these epsilon balls. So they have small variance compared to their magnitude. And so you get a much sharper result by using Bernstein versus using other inequalities like Hofting. So essentially, though, these kind of estimates depend on regularity for the function. So you get the Lipschitz constant of u showing up on the right-hand side. And of course, this uses the Euclidean distance, because that was in the original graph Laplacian. But Euclidean distance is a second-order approximation to geodesic distance locally, and so you can just replace this by geodesic distance, and you get an estimate on the graph Laplacian minus the non-local Laplacian. And it's a high probability estimate. So, and as an aside, this is how you get towards pointwise consistency for the graph Laplacian. So this is not needed for the rest of the talk, but I just wanted to mention this in the slide, is that we have this non-local operator. And essentially now all you have to do is Taylor expand the function u. So if I Taylor expand u inside here, and then I do a bunch of tedious work, and after all the dust settles, what you find is that this non-local Laplacian, it's consistent. It's equal to a constant times this weighted Laplace-Beltrami operator plus an order epsilon error term. And the constant is the only place that the kernel eta shows up. So the constant, I didn't write it down in the slides, but it's like the second moment of eta, roughly speaking. So this, combined with the application of Bernstein on the previous slide, gives you, what we would call pointwise consistency for graph Laplacians. That the difference between the graph Laplacian and the Laplace-Beltrami operator, for a smooth function, that difference is small with high probability. So it's order epsilon plus a parameter t that you can choose. And so one thing to point out is that you need this kind of length scale restriction on epsilon to make these results hold with high probability. So here you would need n epsilon to the m plus 2 to be large, bigger than 1, just for this to be small. But if you wanted an order epsilon rate, so you want to choose this t to be epsilon, then this would be epsilon squared over here. You'd have n epsilon to the m plus 4, much bigger than 1. This is exactly the kind of condition we had in our main theorem statement. Right? But the point of these slides is, okay, these are sort of classical things. So this kind of pointwise consistency goes back to work by people in machine learning, sort of more theoretical people in machine learning, like Hein over a decade ago. And this is for restricting a smooth function with bounded derivatives to the graph. And so, although these results are nice and they can get you pretty far for a lot of analysis of graph Laplacians, they're not useful for us because we're trying to establish that Lipschitzness. So we can't assume that we've restricted a Lipschitz function to the graph. So instead, we have to get our hands a little dirty. We have to find a way to interpolate, sort of extend a function from the graph to the manifold in a way that you can control the non-local Laplacian by the graph Laplacian. And so what we do is actually the sort of simplest thing you try kind of ends up working well. And so what you do is you take for a point x on the manifold, which is not in the graph, let's say, the interpolation of u at that point, so this is I epsilon xn of u, this is just a weighted average of the values of u on the graph at nearby points. And the weighted average is constructed using the same kernel eta that we use for the graph. Okay? And this makes it sort of compatible with the graph Laplacian. So with the definition of this interpolation operator, what we can show is that with high probability, you can do exactly what I was saying, is that the non-local Laplacian of the interpolation is controlled by the graph Laplacian of u plus a small error term, which is just the oscillation of u, okay, over a small ball. If u is Lipschitz, this oscillation term would be like order epsilon, but we don't know at the moment. This is just u is any function on the graph. It doesn't have to be Lipschitz. But okay, so this result is used to prove our main Lipschitz estimate. And once you have the main Lipschitz estimate, you can come back and control the oscillation with our Lipschitz estimate. So you can it's like a feedback loop. And now you can improve that oscillation term to actually order epsilon using the Lipschitz estimate. So this is the sort of true form of the interpolation, is that it's essentially the non-local Laplacian of the interpolation is controlled by the graph Laplacian of u plus an error term. And so once you have this, now you can lift this. This is how you lift the problem to the manifold and end up working only with non-local operators. So let me just give you the main ideas of the proof quickly. Let me see. Okay. So you take the interpolation of u, and I'm going to define eta epsilon to be the rescaled kernel to make things a bit simpler for notation. And then the interpolation is just this weighted average of u. And I'm going to just play this little trick where I replace u by the interpolation of u plus u minus the interpolation of u. That's f. F is u minus the interpolation. Nothing has changed here. But now I split off the f and the interpolation into two different terms. When I split off this f, I get the interpolation of f. And when I split off the interpolation, I get like a double interpolation, like the interpolation of the interpolation. And the point is I get this double sum, where on the inside of the sum, I can pull all the terms that depend only on the graph together. And I can pull the function u to the outer sum. And now the whole point is that now I can control this quantity using only sort of properties of the graph. I don't have to use any property of the function u. I don't have to assume a priori regularity or anything about u. So just using fairly simple application of Bernstein, like on the previous slides, you can control this sum over quantities on the graph. It's consistent with the integral over the manifold of the same kind of quantity. And then you put pieces back together. So then you bring the sum over k back inside, and you bring u of k back inside, u of xk, and what you get inside looks like the interpolation operator again. So you get back the interpolation. And so what you've got is sort of somehow that the interpolation operator plays nicely with this non-local Laplacian structure. Okay. Um, and so this is the essence of the proof. And it's like all of the probabilistic estimates come in this step, going from here with these wiggly lines, where you control this quantity that depends only on the graph. Okay. So this is the idea for this proof. I'll maybe skip this slide. So now that we have this estimate, the question is, okay, so now we can sort of pretend that we can put ourselves in the setting where I have a solution sort of this non-local Laplace equation on the manifold, and I want to prove Lipschitzness. So if I rewrite this non-local Laplacian, it looks like a mean value property for u. So u is equal to an average of u, averaged by this kernel eta and the density rho, plus epsilon squared f of x. And what we prove is that for solutions of this mean value, this mean value property, solutions u are Lipschitz with a constant that depends on the infinity norms of u and f, and it's approximate Lipschitz with the epsilon term. And as I mentioned before, the proof of this uses these coupled random walk methods with ideas that date back to the Linville-Rogers work. Their work was in the diffusion process setting, but the ideas are similar for random walks. We've learned recently that this is somehow equivalent to this idea in the viscosity solution literature, where you double the variables and look at an equation for u of x minus u of y in the product space. And you build a sort of suitable super solution to this equation to bound u of x minus u of y. Somehow these two methods are sort of roughly equivalent at some high level. I like the coupled random walk approach. It's very elegant, I think, and I only learned about this very recently. So I thought I would give a couple of slides to describe how this works. And I want to do it just for a very simple equation. So say it's just the standard mean value property. I have a function u on RD, let's say, and it satisfies the mean value property for a fixed epsilon, but for every ball. And epsilon's fixed and small, right? If epsilon could be anything, I would just, for estimating ux minus uy, I would take large balls around x and y, so they overlap. I would take the difference of mean value properties. It would be great, right? But because epsilon's small, I can't do that. Epsilon's small and just fixed. Okay, so let's just center ourselves a bit so it's easier to write these things down. We'll just say that x and y are two antipodal points, just t times the basis vector ed and minus t times ed, just to make it easier to write things down. The coupled random walks that we use are, okay, we have a simple random walk xk, where the increments are epsilon times these uks, where the uks are IID random variables, uniform on the ball of radius 1 at the origin. The yks have the same distribution, right? But the increments have been reflected about the ed direction. Okay, so the walks are coupled, but they are both simple random walks with the same distributions. We stop the walks when either they come close together on the plane where xd is equal to 0, or when they drift far apart, they get outside of a ball of radius r. So the picture is that we stop in either one of two conditions. So I have these 2 points x and y, and I have these coupled walks, which are basically just reflection around the plane xd is equal to 0, and I stop when either they drift apart and hit the boundary of this ball of radius r, or they come within epsilon over 2 of the half space here. And since u has the mean value property, u of xk and u of yk, so u along these walks, this is a martingale. So you can apply optional stopping and get that the difference u of x minus u of y is the expectation of the difference at the stopping time. And this is the key, is that now you have to look at the stopping time, and what you want is the picture on the right side where they're close when they stop, and you don't want them to be far apart like this. So first, if they hit the boundary of the ball, what you do is you estimate this difference, u of x minus u of y. You estimate it by something very simple, just 2 times the infinity norm of u. Okay, and you can easily estimate the probability that this event occurs with very simple martingale arguments. It scales like the distance between x and y divided by r. So all you're looking at here is, for a single random walk starting at x, what's the probability that it hits the boundary of the ball before it hits this half space? Right? And this is where you get the Lipschitz estimate from for this term, at least. So this is the Lipschitz part, x minus y. For the other piece, you have to be a bit more clever. And what you do is you bound the expectation at the stopping time, because the walks are close within epsilon at the stopping time. You can bound it by the supremum of differences ux minus uy over points that are close within epsilon. And we think of that as like an error term. So now, using this optional stopping and splitting into two cases, I get a Lipschitz estimate plus an error term, right? And the rest of the proof is to show that this error term is actually an error. It's actually order epsilon, right? And so, the idea here is to show this. You actually use the mean value property now, or you sort of directly use the mean value property, because you're now working with points that are close together with an order epsilon. The mean value balls do overlap, and you can just do the usual argument where you subtract the two mean value properties, and you get this sort of contraction factor, because you've cut out the middle of this ball and you're just integrating over a partial ball. So you get this contraction factor, which in the end lets you sort of absorb the term back in the left-hand side. And you get that this is actually an error term, and you finish your estimate and so on. So I'll skip the rest of the details maybe for the sake of time. Let me just say that this extends to having a source term very easily. If you want to read about this this setup in the simple random walk case, there's a recent paper by Leviska and Perez which has this setup in it. For us, we have this drift term that's induced by rho that we have to handle. And so essentially what one does is treats this as like a mixture process. So if I expand rho in a Taylor series, I get, and then I divide rho of x through, I get a term that's a 1, which gives me like a symmetric random walk step. And I get this small linear term, which gives me a non-symmetric random walk step. And if I sort of massage things in the right way, I can think of this as like a convex combination of the symmetric step with a non-symmetric step. And so the coupled walks are constructed by a mixture process, mixing together a symmetric step with a non-symmetric step. For the sake of time, let me just say that you have to couple everything in this stuff. So when you build the walk and the coupled walk, you use all of the same ingredients, but you have to reflect the symmetric part of the increment, whereas you just rotate the non-symmetric part. Okay? So when you build the walks in this way, so these are coupled walks that satisfy the right martingale property. So it means that they sort of average out nicely along the walk, and so the rest of the argument goes the same as in the simple random walk setting. And so then you have to lift this to the manifold, and so there are some ideas here that maybe I'll skip, but you have to essentially figure out how this reflection thing works in the manifold. But this has been done in some form by other people before, I think, and so you essentially have to look at parallel transport of the increments along geodesics and so on. And so your coupled random walk construction looks fairly similar, but now the random walk increments are sampled from the tangent space, and then you flow along geodesics in those directions. And you have parallel transport of the increments from xk over to yk, and so on. But let me just spend the last 5 to 7 minutes here talking about future work. I'd like to get to this stuff. So there's lots of very sort of straightforward applications of these kinds of estimates. So for instance, you can look at other ways to normalize the graph Laplacian. So you could take the random walk Laplacian, or you could take the normalized graph Laplacian. And these are just two popular ways. There are lots of other ways that the graph Laplacian can be normalized. There's actually a whole family of normalizations that just take different powers of these degrees, let's say. We expect that the results will go through for different normalizations. It turns out that this second one, I guess, this normalized graph Laplacian, is one of the more common ones used in practice in like spectral clustering, for instance. We're interested in, this Lipschitz result was only sort of a first result in this direction. We'd like to look at other kinds of regularity results for elliptic PDEs and if they can be extended to graphs, especially higher order things like C1 alpha results. There are lots of other problems, so we've only looked at applications to spectral convergence, but there are lots of problems in semi-supervised learning where you have some kind of Laplacian regularization, and we expect that these kinds of estimates will be very useful for proving or for doing useful analysis for these problems. And finally, I want to talk about extensions of these results to smaller length scales. So throughout the talk, I've sort of pointed out that we have these length scale restrictions on the bandwidth of the graph. And in practice, you want to use the sparsest graph possible. So you want to just make epsilon large enough, probably it's, locally tuned as a k-nearest neighbor graph, but even if it's not, you want to choose epsilon as small as possible. So you connect the graph, you just barely connect it, but you have a sparse graph. And lots of these results don't hold in that sparse setting because there's this lower bound to epsilon that's required. And I think in this setting, we're going to require some ideas from homogenization or percolation theory. And I want to talk about this for the last couple of minutes of the talk. So the length scale regimes that we've seen so far are to get pointwise consistency of graph Laplacians is this n epsilon to the m plus 2. So m is the dimension of the underlying manifold. This should be bigger than log n, let's say. And so this gives me a lower bound for epsilon that looks like 1 over n to the 1 over m plus 2 up to log factors. If you want an order epsilon rate, and so all the results in our paper as well require this to be m plus 4. So this is a larger upper bound or a larger lower bound for the bandwidth epsilon. But it's widely known, these are very old results, that the random geometric graph is connected with high probability when just the number of neighbors, so this is n epsilon to the m, number of neighbors of any given point is bigger than a constant log n. Okay, and so these exponents really they could be as small as 1 over m, and we still have a connected graph with nice properties. And so there's a constant, there's a unique sort of threshold constant at which below that the graph is with high probability disconnected, and above it is connected. And so it's interesting to ask, the first question is, what can you say about all these results, these pointwise consistency or all of these Lipschitz results and so on? What can you say in these much smaller length scale regimes where you're almost at the graph connectivity threshold and you're much smaller than the lower bounds we have in this paper? And even what can you say at the very smallest length scales where the graph is, say, disconnected, but it has a giant component? Which is kind of like a supercritical percolation cluster, for instance. We expect that even in these cases that on the giant component, the spectral properties of the graph Laplacian might still be nicely behaved. You might have Lipschitz regularity and even spectral convergence, but these things are not known. So, for instance, for question 1, there are some answers to this for other problems, and even for spectral convergence. If you use this gamma convergence framework, which has to do with consistency, sort of for first order variational energies, you don't need the lower bound that we had for pointwise consistency, and this gamma convergence framework of sub-7 and Trelos, which has been used by lots of other people since, it can be pushed all the way down to the connectivity threshold for the graph, but variational rates are not as sharp as PDE rates. So you get sort of, this isn't exactly even right. So the rate sort of disappears as you go down to the graph connectivity threshold, but it's sort of essentially order root epsilon, these rates. So the question is, do we expect better rates, and can we prove better rates at these very, very small length scales? Numerically, we see excellent convergence rates. We see second order convergence rates at very small length scales. So this is an experiment on the sphere. It's a 2-sphere, so we're just converging to spherical harmonics. And I take a length scale with m over 2, which is sort of smack in the middle here, where we don't even have pointwise consistency, much less with a rate, but we still see second order convergence of all the graph Laplacian eigenfunctions up to 16 eigenfunctions. So let me just give an idea of what might be going on here and what the future direction would be. So, you don't have pointwise consistency for the graph Laplacian, but our idea is that we should be able to build some other graph Laplacians that are sort of homogenized Laplacians on larger length scales that are consistent, and then use these instead. So the idea is to start with a graph harmonic function, just to make things easy at first, take a random walk on the graph, And then U applied to xk, because U is graph harmonic, U of xk is a martingale. And so U of x is equal to expectation at the stopping time. And rearrange this, it's essentially a graph Laplacian. This is the main observation, is that Lk of U, which is given by expectation of this difference, it's a graph Laplacian essentially because if I write out the expectation, it's just a sum of these k-step transition probabilities. And so these are the weights for the graph Laplacian. And so if the function is graph harmonic, then it's also harmonic with respect to all of these graph Laplacians Lk with larger and larger length scales. And so if we could understand this heat kernel well on the graph with very small length scales, we could prove consistency for these, I would say, homogenized graph Laplacians, and this would allow us to sort of push a lot of these results down to much smaller length scales. But this would require, let me just go down to the end of the last slide, we sort of have worked out what these effective homogenized length scales should be. And even at the graph connectivity threshold, the homogenized length scale is still really good. It's like a fractional power of epsilon, but it's m over m plus 4. So in high dimension, it's even close to linear, let's say. And so if we could prove Gaussian estimates on this heat kernel on the random geometric graph for very small epsilon, we could push all of these results to much smaller length scales. And now let me say, we're not experts on this kind of stuff. So maybe people in the audience are have more familiarity with these kinds of results. I know that there are estimates on heat kernels for supercritical percolation clusters or for problems like this, but we haven't seen anything exactly in our setting yet. So we think we might have to adapt some of these results. But let me stop there, and I'm happy to answer questions.